Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our previous lecture, we discussed about the various types of optimizers and the mathematical equations behind them. And in today's lecture, we will talk about the regularization techniques in neural network. Okay. So the contents of today's discussion are: what is regularization, methods of regularization, under which we will learn about L1 and L2 regularization, data augmentation, early stopping and dropout mechanism. So, we will go forward. Now, what exactly is regularization? Regularization is a set of methods for reducing overfitting in machine learning models. Okay, so they are a set of methods which reduces the overfitting. Now, what exactly this overfitting means? Suppose I have a data set like this, and the red points are the data points, and I have the green line which is the best fit line. And if I see here, this line is not at all fitting the data points. Okay. So, this is the case which we call as underfitting. That means your model is not well equipped enough or not complex enough to see or to learn the pattern that is present in the data. Okay. Now, let's look at this next figure, where this green line is the fitted line, and you see it goes through all the points. But if you see here, this is something, the model is not learning only the pattern, but it is actually learning the noise also. Unnecessary information also it is learning. So, this is called as overfitting. Okay. And then we have this curve here, where this green line is the good fit, okay, or correct fitting. So, lot of times what happens is, the machine learning model or the deep learning model, they tend to overfit the data, okay, and there should be processes which reduces this overfitting. Why? Because if we do not reduce the overfitting, it will do very good in the training data set, but when we give it for unseen data, it will not perform that good, because unseen data it will not be able to generalize. Okay. So, that is overfitting, and we need to avoid being the model getting overfitted. So, overfitting occurs when a machine learning model learns not only the true patterns in the training data, but also the noise and the random variations, like what has happened here in the second figure. As a result, the model performs well on the training set, but fails to generalize effectively to new and unseen data. Okay. Now, we will look into the various types of regularization. The first one is the L1 regularization, we call as lasso regression also, and we will just have a look what is the meaning of this lasso, from where it comes. So, lasso is basically list, absolute, shrinkage and selection operator. Okay. So, list, absolute, shrinkage, selection operator. Now, from where this list term is coming? List is the least absolute error. Shrinkage means, absolute shrinkage means reducing some weights to 0. Okay. And when we reduce some weights to 0, basically we are doing a feature selection. We are neglecting some features in the data set which are not giving that much of information. And then selection operator only keep the features which are relevant, only keeping the key features within the model. And this helps, or this feature selection helps in reducing the overfitting. Okay. Now, the core idea is, reduces L1 regularization or lasso regression reduces overfitting by simplifying the model. So, what exactly is happening when we reduce some weights to 0? When we reduce some weights to 0, that means we are taking out some of the features from the data set which are not very relevant, and this makes the model simple. Okay. more complex the model is, the more the tendency of getting overfitted. Okay. Simplifies the model by shrinking some of the weights to 0. And this is done, how it is done? By adding a penalty term. So, there is a penalty to the loss function that is proportional to the sum of the absolute values of the model's coefficient. In this case, it is the weights. Okay. So, what we do is, we have the loss function. To that loss function, we add some penalty term that is proportional to the sum of the absolute values of the model. Okay. We will see how it is. So, the equation for L1 regularization goes like this: L1, the loss in L1 regularized model is equal to the loss, the normal loss, plus lambda into lambda summation over I, the absolute values of omega I. Okay. So, now this is basically the lambda into summation of absolute value of omega I is called as the penalty term, and this penalty term actually, this is the L1 norm of a vector. Okay. And lambda is, what is lambda? Lambda is a hyperparameter which decides the strength of regularization, how much we want to regularize. Okay. So, we will quickly have a look into what is this L1 and L2 norm of a vector, because I have spoken about that one, L1 norm. So, if we have a vector x equal to, it is a vector and minus 3, 4, 5 and minus 2 are the values. L1 norm is basically, it is the addition of all the absolute values. Okay. So, absolute value of minus 3, 4, 5 and minus 2, and then sum of that one. Whereas L2 norm of x is given by the square root of the sum of the squares. So, that is L2 norm. Now, so how L1 regularization helps in feature selection, that we will see. Now, we have seen the penalty term here is lambda into summation of the absolute value of the weights. Okay. Now, the derivative of the penalty term in the loss function is a constant, which means what? Suppose we take the loss function of the L1 regularized form. Okay. And then for getting to the convergence, we usually take the derivative, right, of the loss function with respect to the weights. Now, if we take the derivative here, your penalty term is having a absolute value of omega I. So, when you take the derivative, the derivative is a constant value. Okay. So, what happens due to this? This constant derivative means L1 aggressively pulls the weight towards 0 with the same strength until they become exactly 0. So, it is directly proportional to the strength. Okay. So, it is directly proportional to the strength of the regularizing parameter, hyperparameter. Okay. When any weight is 0, that feature is removed from that network. So, in L1 regularization, what can happen is, it can reduce the weight exactly to 0, and when the weight becomes exactly 0, then what happens? That feature gets removed from the equation. Okay. Removed from the network. Now, we will see what is this L2 regularization. In L2 regularization, we have the loss of L2 regularized equation, the loss of L2 regularized form is equal to loss in the normal form plus lambda into summation over I Wi square. So, we are taking the square values and then square of the weights, and then we are taking the summation. Okay. Now, this is the penalty term here, and this, in this L2 regularization, it adds the squared value of each coefficient as a penalty term to the loss function. Okay. Now, we will see what is the difference that is coming because of this squared term in the loss function. Okay, in L2 regularization compared to L1. Unlike L1 regularization, L2 regularization cannot reduce coefficient values exactly to 0. It can reduce the weights nearly to 0. So, in L1 regularization, what we told is the weight can come down exactly to 0, because when we take the derivative of the penalty term, that becomes a constant, and when it is a constant, it is proportional only to the hyperparameter lambda. It has nothing to do with the weight value. Okay, so we can pull it down till 0. Now, in case of L2 regularization, we are unable to do this one. We are unable to get into a point where the weight is exactly equal to 0. We can bring it down near to 0, but not exactly 0. That means L2 regularization cannot perform feature selection. Okay, L2 regularization cannot do feature selection. Now we have to see why it cannot do a feature selection, or why it cannot take the weight exactly to 0. So, in L2 regularization, the penalty term is, lambda into summation of omega I square. Now, if we take the penalty term's derivative, there is 2 into lambda into omega I. Now, what happens? There is a dependency of this omega, of this weight W, not omega, W. Okay. So, the force pulling the weight towards 0 is proportional to the weight's current value. So, there is a dependency of the weight. The force pulling the weight towards 0 is actually proportional to the weight's current value. And the weight, when the weight is close to 0, the force pulling it to 0 also becomes very small. Okay. So, because there is a proportionality, this term is there, which was not there in case of L1 regularization, and this prevents it from reaching to 0. So, always, however small the weight is, the force pulling it also becomes small, but it cannot go to 0. Okay. So, this is the reason why L2 regularization cannot perform feature selection. Now, there is another difference between L1 and L2 regularization is, L2 regularization is not robust to outliers. Now, why it is this one? What is an outlier? Suppose we have a data point, something like this. Okay, some data points are here, and one data point is somewhere here. So, this is completely outside the pattern, and this is called as the outlier. Correct? Now, what happens in case of L2 regularization? It amplifies the error that is coming from the outlier point. What happens here is, this is your penalty term here is proportional to Wi square, and when you have an outlier point, the error coming from that outlier point is high, and when we square it out, it amplifies the error that is coming from the outlier point. And what does the model do? The model tries to adjust to accommodate this outlier, instead of leaving it aside, telling that no, this is something which is not a part of my major portion of the data set. It tries to accommodate the outlier. Okay. In L1 regularization, what happens is, it is the penalty term is proportional to the absolute value of omega i's summation. Okay. Now, here the penalty is proportional to the absolute value of the weights, and hence does not amplify the error coming from the outlier. So, whenever there is a square term, it gets amplified, and whenever there is absolute value taken, it is proportional to the absolute value of the weight. The penalty is proportional to the absolute value of the weight, and hence there is no amplification that is happening for the errors that are coming from the outliers. Okay. Now, till now we have learnt about L1 and L2 regularizations, and we will see how and when should we choose L1 and when should we choose L2 regularization. The first thing to look into while choosing this regularization technique is the data set and the final goal of the analysis. If data is high dimensional with multiple features, like healthcare data set, they have multiple numerous features, then L1 regularization is preferred, as it can do feature selection leading to a sparse model. more the less complex the model is, better it is for achieving your convergence. If the data set contains highly correlated features like multicollinearity, that means there is a lot of interrelationship between the features, example in financial data sets, then you can go for L2 regularization because it encourages small but non-zero coefficients. It will never take out any feature from the data set and this is very important for data sets which are having highly correlated features. If you take out one feature, that correlation gets hampered, okay, and the prediction will not be correct prediction. So, L2 regularization can be more suitable in case of data sets which are highly correlated. Now, we are done with L1 and L2 regularization. Then we look into another type of regularization technique which is called as the data augmentation technique. What is this data augmentation technique? It is creating new training samples by applying random transformation to your existing data. Label invariant transformation, that means the label is same, a cat's image remains as cat's image, but you do lot of transformations to that image so that we get more number of training samples. Like for example, this is an original image is of a cat, and if you see there is a horizontal flip, there is a vertical flip, then 45-degree rotation, minus 45 rotation, then it blurring, then brighter, noise added, darker, you know, then grayscale, it has become from color to grayscale, and then cropping it out. So, all these are augmented data. From one original data, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, you know, data which are label invariant transformations of your original data. So, this data augmentation is a technique where we can use various kind of transformations to improve the data size. Now, the transformations, as I told, it can consist of rotation, cropping, flipping, scaling, color space augmentation like brightness, saturation, contrast, enhancement, decreasing the contrast. All these things can be a set of transformations. Now, the question is, fine, I have got an augmented data set, but how it helps in reducing the overfitting, how it regularizes, okay. So, the question here is how it helps in regularization. So, neural network generalizes better as it gets exposed to more diverse set of training examples, thus preventing overfitting. So, more the number of data sets coming from diverse environment or diverse what I should say diverse conditions, more the model's output is generalized, okay. And as deep neural network requires a large training data set, data augmentation is also helpful when we have insufficient data to train a neural network. So, two things. One is we are taking diverse set of data while we are augmenting using data augmentation technique, and this helps the neural network to generalize more to unseen data. Also, in deep neural network, we require a lot of training data, and wherever there is a crunch in data set, we can use these data augmentation techniques which will help the model to be trained better, okay. So, this is about data augmentation. Then we come to something called as the early stopping. Now, what is this early stopping? We have a curve here. X axis we have the number of epochs and y axis is the loss or the error. Now, you have two curves here. One is the training loss curve, another one is the validation loss curve. Now, what is the validation loss curve? What is validation, training and validation we tell when we work with neural networks. So, training is basically training your model with all data set that you have, and validation is actually done to see how your model is actually generalizing to unseen data, okay. Now, if you see the pattern here, your training loss is coming down with the number of epochs, whereas your validation loss, after it initially it comes down and then it starts going up. Okay. So, this is the point where, if you see, this is the point where your training loss and your validation loss actually is minimum, and after that your validation loss increases, but your training loss goes on decreasing. That means what is happening here is, after this point, after these number of epochs, it may be 50, 100, 150, whatever, what is happening is your model is getting trained, and it is trained so much that it is learning the noise also that is present in the data set, training data set, which due to which it is not able to generalize and your validation loss is going up. Okay. So, basically we are not improving the performance after this number of epochs. Okay. This is the place where exactly it is overfitting. Okay. So, this is the place, if you continue, it is the place where the model is overfitting. Okay. So, validation loss evaluates the model's performance on portion of the data set that the model has never seen during training. Okay. And early stopping is the process by which we monitor the validation loss during the training, and then we stop the training process from at the point where validation loss becomes minimum and it does not keep on increasing. Okay. If the validation loss fails to decrease for a predefined number of epochs, we refer to as patience. A lot of times we use this term patience. Training is halted, because once the training is halted, we can be assured that there is no overfitting. This ensures that the model is captured at the point where it achieves optimal performance on unseen data, preventing overfitting while reducing unnecessary computation. Because if we keep on increasing the number of epochs, it is overfitting. It is not giving me any good results after, because overfitting means it will not generalize to unseen data, but at the same time the computational cost becomes huge. So, that can be avoided by the process of early stopping. Okay. So, we are halting the training at a place where your validation loss is minimum. And how do we do this one? We run the validation set evaluation periodically. After few epochs of training, 2-3 epochs of training, we do one validation loss check. Again, we do it in a periodic way and choose the stopping time based on the validation loss. Okay. So, this is about early stopping. Then we come to another regularizing technique, which is called as dropouts. Now, what is this dropout? Suppose we have a neural network like this. These are the input neurons, these are the hidden neurons, and then you have the output neuron here. Okay. And during the training phase, during each iteration of training phase, we randomly drop or set to 0 a fraction of the neurons in the network with some probability. So, what exactly we are doing here? We have all these neurons, right? So, whichever are the dotted ones, we have dropped them or we have set them to 0. Why? What is the advantage of doing this one? So, these are dotted ones are the deactivated neuron. It ensures that the network does not become overly reliant on some particular neurons. So, randomly we will drop some neurons from the network, and this is called as the thinned network. Okay. If there are n nodes in a network, then 2 to the power of n network configurations or thinned networks are possible. So, like this, you can randomly pick some neurons, deactivate them, and do this one during the training phase only. Okay. So, we will have a look how this process flow of dropout regularization happens. So, during the training time, we define a dropout rate or dropout probability, which is P. Okay. Then we create a dropout mask D for each layer with random values either 0 or 1. Okay. We will see with an example, it will become more clear. Apply the mask to the layers activation by element wise multiplication. So, whatever the neurons are active, we put the mask over that one. This makes some of the neurons inactive in the network, making it the first thin network. Then scale the remaining activations by a factor 1 divided by 1 minus p. We will come into why we are doing that one. Check with the edges which are present in this thin network, update the weights associated only with those edges, and iterate the process for another thinned network. Okay. So, we will have a look into how it is done in my next slide. This is done during the training phase. During testing, deactivate the dropping mechanism. So, dropout mechanism. We do not want any dropouts to be there during the testing phase, and do not apply any scaling. So, whatever dropout mechanism or whatever scaling we are doing that one only during the training phase. Now, the question is how dropout is preventing the overfitting. During training, neurons are removed randomly, thus preventing overtuning of any node to achieve the minimum cost function. So, there should not be too much of importance given to a neuron, and your output should not be too much dependent on one particular neuron. If we randomly pick out neurons and deactivate that one, that can be avoided. An ensemble of small neural networks or thinned models with different structures are trained during each iteration, which improves the model's capability to generalize to unseen data. So, when we are during the training phase, we are getting an ensemble of different structures of the network. Sometimes first neuron is deactivated, next time the second neuron of the hidden layer is deactivated, third time maybe one of the very inner hidden layers, there some of the neurons are deactivated. So, we have a bunch of thinned models with different structures, and an ensemble of those small networks are trained during each iteration, which improves the model's capability to generalize the unseen data. Now, what is a limitation of dropout regularization? It increases the training time, because we are taking the ensemble and then we are doing it, so increases the training time. Now, we will have a look into example of dropout regularization. So, we have a neural network like this, and suppose our x vector is given as 2 minus 1.5, okay, transpose of that vector. Now, the dropout probability p equal to 0.2. So, with probability 0.2, we will drop out those neurons. Okay. So, if the dropout probability is 0.2, then the keep probability will be 1 minus p, which is 0.8. So, for any neuron, the dropout probability is 0.2 and the keeping probability is 0.8. Okay. Now, let us make a mask which is equal to like this 1, 0, 1. What does it mean? 1 means it will be an active neuron, this will be a deactivated neuron, and this is once again the neuron will be active. Okay. After application of the mask, what happens? Your x, how does your x look like now? The first term is there, second term becomes 0, and third term is there. Okay. So, we have made a mask like this 1, 0, 1. If the mask is like 0, 0, 1, then we get x equal to 0, 0.5. Okay. I hope that is clear. And then we do a scaling. Now, where we are doing a scaling? We are doing the scaling for the neurons output which are present in the thinned network now. Okay. So, how do we do the scaling? It is x equal to 1 by 8 of 1 by 0.8, from where we are getting this is 1 by 1 minus p to 0.5, which is becoming something like this 2.50, 0.625. Okay. So, so this is the scaled value of your inputs now. Now, the question comes, why do we do this scaling? We do this scaling because during the testing time, we are not doing any dropout. We are keeping all the neurons intact. So, in order to avoid that mismatch between the outputs during the training and test time, we scale the output of the neurons that are alive or active in the thin network by a factor 1 by 1 minus p. Okay. So, this is the way we do the dropout regularization, and as I told, this dropout regularization techniques allows us to avoid the tendency of overfitting. Okay. So, with this one, I come to the end of this lecture. Let us, before ending the session, let me have a summary of what all we have learnt in this session. So, we started with what exactly is the regularization technique, why do we do it? So, regularization is basically nothing but it is the process by which we reduce the tendency of a model to overfit the data, because if there is an overfitting of data, the model will not generalize well to unseen data set. It will do very well in training data set, but during unseen data, when you show unseen data to that model, it will not do good. The performance will get hampered. The performance will not be good. So, that is and we need to do something, and these regularization techniques are the techniques which are used for avoiding this overfitting. Now, we have seen what is this L1 regularization and L2 regularization. In L1 and L2, we have seen there is a penalty term that is added to the loss function, and this in L1 regularization, that penalty term is proportional to the summation of the absolute values of the weights, whereas in L2 regularization, they are proportional to the summation of the square of the value of the weights. Now, this penalty term actually reduces, or it, due to this in L1 regularization, what happens is it can bring some of the weights to 0, exactly to 0, which is not possible in L2 regularization, because in L1 regularization what we do is as our loss term or the penalty term in the loss function is proportional to the absolute value of the weight, summation of the absolute values of the weights. When we take a derivative of the loss function, then regularized form of the loss function, then this derivative of this absolute value, they become constant, and whenever this is constant, it is not proportional to the present weights value. So, what happens is it is only proportional to the lambda term, which is the strength of regularization, which we have seen in the equation, and we can pull down the lambda term can be so strong that it can pull down any weight to 0, and thus it helps in feature selection. And when we do a feature selection in L1 regularization, we are actually doing actually making a model which is very simplified model, and which reduces the tendency of overfitting. More complex a model is, the more the tendency of overfitting. In case of L2 regularization, this is not possible because the derivative of the squared term, when we take the derivative, there is a W term, weight term that is there in the derivative. So, even when you reduce the weight value, what happens is your derivative term is also getting reduced, but it is never coming to 0. So, the thing is, we cannot make the weight exactly to 0, we cannot bring down the weight of any feature exactly to 0, because the derivative, there is a proportionality with the weights, current weight value. And then we have seen that the robustness of L1 and L2 regularization techniques with outliers, okay, with respect to outliers. So, we have seen in case of L2 regularization, there is, as there is a dependence of to the square of the gradient terms, it tries to amplify the error that comes from the outlier points, because for outlier points the error is always high, and because there is a square term in that weight, it amplifies that error term, the error that is coming from the outlier, which is not the case in case of L1 regularization, because it is proportional to the weight value, the absolute value of the weight. So, L2 is not robust to outliers where L1 is. And then we have come to other regularization techniques like data augmentation, where we take an original image we give some lot of transformations like vertical, horizontal, flip, 40 angle rotations, 45-degree angle rotation, minus 45-degree angle rotation, then cropping, and then changing the color from color to grayscale, or making the contrast bright, contrast mode, making it more brighter, making it blur. So all these transformations are made so that we get a augmented data set. So from one image we can kill multiple, a set of multiple images. And how it helps in regularization is, more the number of data that is coming from diverse background, more is the likelihood of the network to generalize to normal, to unseen data. So the tendency of overfitting will get reduced in this case. Also, data augmentation helps in deep neural networks where we require lot of data to train our models. Then we have looked into early stopping, in which we have seen the training loss and the validation loss curves. And early stopping is a process by which we have seen that we halt the training process at the place where validation loss is minimum. Okay, so that is early stopping because it reduces the tendency of overfitting, and also it reduces the time complexity. And then we have looked into dropout regularization. What is this dropout regularization? It is nothing but in a neural network, we deactivate some of the neurons in random way. And then we take those, we call them as thin network, and those thin networks we train, and we take the output, and in each iteration we will have these various structures of these thin networks. And what happens due to this thinning or making deactivated neurons is that there is the possibility of the model over relying on any particular neuron gets reduced. Okay, so that is what we do in dropout regularization, and the dropout mechanism is used in training phase, not in the test phase. During testing time, we don't do any dropout, we don't drop out any neurons. At the same time, we don't scale the outputs also, which is done during the training time. The scaling is done because we don't want the mismatch of the outputs between the test and the training time. So because during the testing time you are taking all the neurons output, whereas during the training time some of the neurons are deactivated, so we scale the whatever active neurons are there, we scale their output in that way. Okay, and we scale the outputs in that way, and that helps in avoiding overfitting. So with this one, I come to the end of today's session. I hope you all have understood the regularization techniques which are used in deep learning. And in the next session, we will have a hands-on session on multilayer perceptrons, where you will use various kinds of optimizers as well as regularization techniques. And I hope you understood the concept, how these optimizers or the regularization techniques are used in neural networks. That's all for today's session, and I conclude today's session. So happy learning till we meet the next time. Thank you all.